Welcome. In the previous video, we learned about the use of superposition to aggregate the deflection of different load cases to figure out the deflection of the beam under collective application of these load cases. And we'll use what we learned from this video, the superposition method application in beam deflections, to figure out how to solve statically indeterminate beams. And we use this concept superposition to solve statically indeterminate axially loaded members. So it's not a new concept to us, but we'll see here how to use the superposition method very efficiently in this case, because the calculation of beam deflections are more complicated and requires more work, the integration method, compared to deflections of axially loaded members. So we need to do it in a smart way, in an efficient way, which is the tables way. So we have here this beam is fixed at A and it's supported by a roller at B. And you can see here this is statically indeterminate beam because it can sustain itself by just support A. It can be stable by being just a cantilever beam fixed at A, and point B will be just free. But here kind of I added an additional support at B, and that makes it statically indeterminate. There are 3 reactions at A and 1 reaction at B, 4 reactions, 4 unknowns total. And I have only 3 equilibrium equations in the 2D equilibrium of this beam. And this beam is loaded with a moment load, MO. So this MO is a load, not a reaction. So there is a moment reaction at A, but this beam is loaded with a moment load. Just to give you an idea what can this moment load look like. So if this is the beam, and this is my hand, the rotation of the hand would create a moment at the tip of the beam. So in real life, there are different ways of calculating a point load, point moment. So I will not go in detail on that, but it can exist actually having a moment load, point moment load at beams. And we want to solve for this beam. So the first thing to be able to design the beam is to figure out the external equilibrium, calculate the reactions on the beam, and then I will be able to calculate the internal forces on the beam, and then the stresses at points and principal stresses and all of that fun stuff. So we are stuck at the first step and we don't know really how to solve. We have 4 unknowns, 3 equations. And then deflections or strength of materials will come to save us here. So we'll use the superposition method to turn one of the redundant support reactions, the one reaction support that I don't really need for stability, and I will apply it on a second load case as a load. So here I decided to loosen the constraint at point B, so I remove the constraint there and leave it free, and the first load case here is basically taking the original load that I have, which is MO, on that relaxed statically determinate beam, and then use that same statically determinate beam to reflect now the reaction that I removed, that redundant force or redundant support reaction that I removed, which is By in this case. And then when I add these two together, I will get back to my original beam AB that's fixed at A and supported by a roller at B. And now the idea is I will apply compatibility condition by observing the deflections that happen at point B. So the moment here will cause deflection downward, kind of guessing or feeling that if this is fixed, so this is fixed here, and this moment here is causing rotation like that, so typically it will go downward with this clockwise moment. While the reaction By, I assumed it to be going upward, so I applied upward on the second load case of the beam, and that means it will push the beam up. So now from compatibility, point B is supported by a roller, so this means the vertical movement of the beam at this point is constrained by the support, so whatever new or deflection in the first and the second load case, when I add them together, they should add up to 0. So new parentheses L here means it's the deflection of the beam at x distance equal to L. So that's just short for that. And the question turns out to be finding the deflection of the beam, nu1 and also nu2, these deflection values for the shown load cases. How to find these? Of course, we can use the integration method, but it's a lot of work. So we learned from the previous video using the tables, the beam deflection tables, especially if these load cases are common load cases that are shown in the textbook tables of the beam deflections. I'm showing here the first 3 columns of one of the possible available tables in textbooks. First one is showing the load cases, second is the maximum slope that happens, and the third is the maximum deflection that happens. And you can see for this table here showing cantilevered beams, and typically the maximum deflection and the slope happens at the tip of this beam. And to match, we need now as the first step to match our 2 load cases with the load cases in the table. And I see here the first and the third one match with my load cases. The third row in the table matches with the first load case, and the first row matches with my second load case. One thing to pay attention to is to match the look and the direction of the load case. So for example, the first load case, where there is a point moment MO, in my real life problem, MO goes clockwise, but the table shows MO to go counterclockwise. It's still matching, but now when I pull nu max, that nu that happens at the same point where I'm interested in, which is the tip of the beam, it shows here in the table it's a positive value because the moment is counterclockwise. In my case, when the moment is clockwise, then I have to flip the sign. So you see here nu1L is equal to nu2 max, which is equal to negative the value that I got from the table, MO L squared divided by 2 EI. And then in the first row of the table, it matches with, it's a force at the tip of a cantilever beam. It matches with my case, the second load case here, but the direction is reversed. So I will reverse the sign that I have from the table. So in the table it's negative. Now I make it a positive, and it's equal to positive PL cubed divided by 3 EI. And P here is, in my original problem, is called BY. And now, when I put these back to the compatibility condition, put their addition and summation to equal to 0, I will figure now, here you go, one reaction, BY. So now I'm down from 4 unknowns to 3 unknowns without even touching the equilibrium equations. And I should be able afterwards to be able to solve all of the unknowns of this beam, the 3 left reactions, by using the 3 equilibrium equations: summation of forces in X, summation of forces in Y, summation of the moments. And this is the free body diagram. And I know now BY is it's not an unknown anymore. I know the value for it, and I will be able to solve for the 3 reactions, which something I will leave for you to have fun with. But now we learn how to use the deformation and deflection information of the beam in our side to be able to solve for whatever unknowns more than I could have be able to solve using equilibrium equations. One thing we have seen in this exercise is you have to pay attention to match the original problem load cases with the table load cases, and match them in terms of description of the load case and the direction of the loads applied. All right, thanks for watching. Take care of yourself, and for those around you, have fun. I will see you in other videos.